All right, let's say we have a simple function y equals sine x. And I want to know the value of y when x. I'm just going to pick a bunch of values for x. Let's do some that we know. Pi by 4, 0, pi by 2. 4/5 we don't know, but we could figure out. Okay, so how would we do that? Well, obviously you just plug in those numbers in for x. So you plug in sine of x, and you're going to get the answer, or sine of pi by 4, you're going to get the answer of 1 over root 2. And there's only one answer that's correct. Why is that? Because this is a function. Functions pass the vertical line test, which means no matter what value I put in, let's say I say pi by 4, if you see, look at pi by 4, there's only one answer that's correct. Right? When I plug in 0, the only answer that's correct is 0. Pi by 2, that's right here. The only answer that's correct is 1. So your calculator is actually correct when it gives you the answers. If you plug in sine of any number, it's actually giving you the correct answer. But what if instead I gave you the other value? So you have your y equals sine x. What if instead I gave you this value? Okay, so now we always say we give the x value, right? So now we're going to say this is the x value. I'm going to say equals sine of y. So I'm giving you the value that's here, what would normally be our y value, and you have to find the x value. Okay, but well, the equation, we'd have to rewrite it. We always like to have y equals. So we take the sine inverse of both sides, and you get the sine inverse of x equals y. So this is our new equation, right? So if I want to say, if I wanted to know what y value, so look right here, what x value would give me a y value of 2/3? Well, then it's kind of like you get this new equation and you plug in an x value right here of 2/3. And all you're doing is a sine inverse. Well, here's the problem. Sine inverse doesn't give you just one answer. So what we really did when we switched the x and the y, when I changed it to x sine y, I changed the equation to its inverse equation, right? Now this is no longer, I can't say it's the inverse function because this is not a function. The answers will be all the same. They're going to match up with the same things, except now, it goes this way. This is not a function. This does not pass the vertical line test, right? At 2/3, now if I plug in 2/3 for x, which is right here, I can get an answer here, 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 here. There are plenty of answers. Now our calculators do a terrible job of that. They just give you the first answer right here. And then we're supposed to find all these other answers, okay? Now why do you not learn this curve in advanced functions? Well, because it's not a function. The inverse equation of y equals sine x is y equals sine inverse of x, and that's the way that we would get all of the answers if we knew the y value and not the x value, right? So basically if we knew the value that was alone and not the value that was inside the sine, right? And we already knew how to do that. We would just do the inverse operation and everything was fine and dandy, but we never really learned about it as a curve that's a non-function because we're not studying non-functions, right? Now if you notice, if I plug in an x, in this case, if I plug in x equals 2, it's just going to give you an error. There are no values in the sine inverse function, so this would be x and this would be y, which is equal to sine inverse of x. It's the inverse function. All right, if I put in a 2 or a -2, it's just going to come up with the error. The only numbers I can put in for sine inverse are between -1 and +1. Try it yourself on your calculator. Anytime you put a number less than -1, it's going to give you an error. Greater than 1 is going to give you an error. Okay, now let's move on to logarithms. Same sort of concept, except your typical exponential, y equals, let's say, e to the x, or let's say 2 to the x, x, y, crosses here at 1, and you got 1 comma 2, You got 2 comma 4, and you got 3 comma 8. I know it's not to scale here. 4 comma 16 would be way up here. All right, now that's y equals 2 to the power of x. So that's assuming that I'm giving you the x value of 0, 1, 2, 3, 4. You put it in your calculator, and it's just going to go 2 to the 0, which is 1, 2 to the 1, which is 2, 2 squared is 4, then 8, then 16. But what if I give you this number? Okay, so since I'm giving you this number, that's really our x, because we always give you the x. And I want to know this number, so that'll be our new y. This is your inverse function. Now notice I didn't call it the inverse equation, because this one actually is a function, right? When your x becomes y and your y becomes x, it's basically just reflecting it in the x equals y line there, and it ends up looking just like this. Okay. And this one just happens to be a function. It passes that vertical line test. Okay, so the inverse of your exponential is called a logarithm, and it's also an exponential. It's just the inverse of it. It's just kind of the reflection of it, but it's still an exponential equation. X equals 2 to the power of y. Now, we always like to isolate the y value, just like when we had x equals sine of y, the inverse function of y equals sine x. Okay, these are inverses of each other. We always like to isolate the y value so that you could just straight up plug in the x and let your calculator do all the work. But when we isolate the y here, we ended up with y. The only way to do it is to take sine inverse of both sides. So y equals the sine inverse of x. I switched the sides too because I want y to the left. Well, how do you do it here? Well, you have to take the logarithm of both sides to get y by itself. So I'm going to say the log of base 2 of x equals the log base 2 of 2 to the y. The log of base 2 is the inverse operation of 2 to the power of something. Okay, so that would bring us just to y equals log base 2 of x. Right? Now, if you plug in a 1, you're going to get 0. If you plug in a 2, you're going to get 1. If you plug in a 4, you're going to get 2. If you plug in an 8, you're going to get 3. If you plug in a 16, you're going to get 4. Okay? So the logarithm with the same base as your exponential will just be kind of like your sine inverse with the sine inverse of your sine curve. Right? Logarithms are exponentials as well, but they're the inverse as of exponentials. Now, the cool thing about logarithms is they are functions. When I plugged in a 1, I didn't get a whole bunch of answers like I did with the sine inverse. Okay, sine inverse is nasty. The logarithm has an equation, or has a graph that goes like this. This is at 1 comma 0. And if you notice, the normal exponential would be 0 comma, we'll go through at 0 comma 1. Right? Here you have, let's say, negative 1 comma 1/2, right? 2 to the power of negative 1. This is 2 to the x. 2 to the power of negative 1 is 1/2. Well, then when I have a 1/2 in here, the answer will be 1/2 comma negative 1. 2 to the negative 2 is 1/4. So at 1/4, you're going to have negative 2. As this gets smaller and smaller and smaller, it approaches negative infinity, and the y value approaches 0. So here, the x value approaches 0 as the y value approaches negative infinity. Right? Over here you have 2 comma 4, because 2 to the power of 2 is 4. Well, then here you have 4 comma 2, because the log, so this is y equals log base 2 of x. The log base 2 of 4 is equal to 2. Right? So it's always the opposite. So basically you're asking yourself, hey, what is 2 to the what is equal to 4? And the answer, 2 to the what equals 4. Whatever that answer is going to be the log base 2 of 4. All right, let's sketch a graph of a few just common log functions. So first I'm going to do a normal exponential function that you guys are used to. So let's call this y equals 4 to the power of x. Let's just quickly do table of values. Let's do x is negative 2, so 4 to the power of negative 2 is 1/16. So negative 2, we have 1/16 right here. Negative 1, you're going to have 1/16. Negative 1, you're just going to have 1/4. Zero, let's make those lower. 1/4 here. 0, you're going to have 1. Anything to the 0, so 4 to the power of 0 is 1. At 1, you're going to have 4 to the power of 1, and you're going to be up to 4. And as we know, exponentials grow real fast. 2 is already going to be at 16. That's off the charts. Okay, so this is going to go up this way and come down this way. All right, well, let's do in blue y equals the log base 4. Notice the base is 4, so their base has to be 4. That's what goes down here, of x. And this is still x. Right now, we plug in a negative 2, you're going to get an error. A negative 1, you're going to get an error. Why is that? Because this y value would never be negative 2 and negative 1. You never end up in this exponential. This y value is never negative. It goes down close to 0, but it never is 0 or a negative. So again, so when x is 0, you get another error. Right? But as soon as x is, I'm going to skip a few. Well, let's go, actually don't skip a few. Let's say x is 1/16. Okay, well, when y was 1/16 here, x was negative 2. So this is going to give you negative 2. When x is 1/4, it's going to give you negative 1. When x is 1, it's going to give you a 0. Okay, so 1/16 is really, really close here, and that's going to give me negative 2. At 1/4, which is about here, I'm going to get negative 1. At 1, I'm going to get 0. At 2, oh gosh, well, that's going to be somewhere in here. So let's skip ahead to 4, because that's going to be an easier one to do. At 4, we're going to get a value of, since this is 1, 4, we're going to get 4, 1. 3, 4. So as you see, this doesn't go up very fast on this side. And it never does get to 0. So your domain is x greater than 0. That's the only domain. Anything less 0 or less, you're just going to get an error. That's not going to work. Right? And the next one, 16, will give you 2. So 4, 5, 6, 7, 8, 9, 10. So it's way off the charts. So it's not even going to get to 2 until you get to 16. Now it will go off to infinity, but it's just going to go a long way before it does. Okay, so you're going to have to go really, really high in the x direction before you get very high at all in the y direction. All right, let's try the inverse of y equals 1/3 to the power of x. So 1/3 to the 0 is 1, obviously. Everything to the 0 is equal to 1. So 1/3 to the 1 is 1/3. So it's smaller. 1/3 squared is 1/9. All right, if you remember, if you have a base that's smaller than 1 but greater than 0, you're going to have a graph that gets closer and closer and closer to 0 as you go to the right. What happens to the left, though? All right, let's see. So we had x. At 0, we had 1. At 1, we had 1/3. At 2, we had 1/9. At 3, we had 1/27, and so on and so forth. But at -1, well, now it's going the other way. We're going to get 3. Okay? It's going to be the reciprocal of to the power of 1. And then, so -1 is 3. So that's 1, 2, 3. That should be up here. All right, -2, that's going to be 9. -3 will be 27. We're getting up real high, real fast already. 9 is going to be way 3, 6, and that's going to be off the screen already. So we're kind of going like this. All right, let's go in red. Let's do the same graph, except or it's on the same axes. Let's do x, and instead of y equals 1/3 of the x, we're going to do y equals log base 1/3 of x. Okay, so log of x with the base of 1/3, and we're going to say okay, when we're going to use these values to plug in for x. So when x is 1, y is 0. There it goes. When x is 1/3, that's when y is 1. So x is 1/3, that's right here, and y is 1. That's right here. When x is 1/9, that's when y is 2. So that's in really close, that's up here. And when x is 1/27, that's when y is 3. That's really, really tight in almost 0. But as you notice, it'll never ever cross this y-axis. Okay, it'll just keep getting in tighter and tighter, and it'll go higher and higher. So there's going to be an asymptote there. It's going to come in here. What happens when x is 2? So that's when, oh, here we have when x is 3, we're going to have y is -1. When x is 9, that's how long it takes for it to get to -2. So 3, 4, 5, 6, 7, 8, 9. It'll be right about here, -2. And it'll take, it's going to be 3 times that, 27, before it gets to -3. So here we go. There you go. So these guys are basically reflections. As you can see, this here is a reflection in the x equals y of this guy. And this part here is a reflection of this guy. Okay, so it's just a reflection in the line x equals y. But basically we're saying the logarithm is the inverse operation of an exponential, just like sine inverse was the inverse operation of sine. The cool thing about logarithms is when you actually put it in your calculator, you can trust its answer, because a logarithm, this is a logarithm with a base that's less than 1. It's going to go through at 1. And this is a logarithm with a base that's more than 1. It's going to go through that way. And you notice they're both functions. They both pass the vertical line test. So any x value that I put in will yield only one y value. So you can trust your calculator. It's not like a sine inverse that goes like this. And when you plug in x is 2/3 or something like that, you get like a whole bunch of different answers, and your calculator only gives you the first one for some reason. All right, so let's say I just give you an exponential. Let's write y equals 10 to the power of x. And I want the inverse function. Well, a really easy way to give the inverse function, I mean, if you want to be tricky, the easiest way to give anyone an inverse function for any function ever is just to switch the x and the y. Y equals 10 to, x equals 10 to the power of y. There's your inverse function. The problem with that is when we ask for functions, we generally want it to be in the form y equals if possible. All right, so how can I do that? Well, I would just have to take the log base 10 of both sides, log base 10 of 10 to the y. And the log base 10 of 10 to the power of something is, since that's just the inverse operation, that's just equal to itself, y. So log y equals a log base 10 of x. Now, I didn't write base 10 this time, and that's because just like square root, if you don't write anything, we just assume that it's a 2. Well, for log, if you don't write anything, then everyone just assumes it's a 10. It's just, if you type in log on your calculator, that'll be log base 10. All right, so this is just log at y equals log of x, and we just assume that's base 10. All right, let's try another one. If I give you y equals 6 to the power of x, well, and I ask you for the inverse function, well, there are two answers. X equals 6 to the y, done, correct. But if I want you to isolate y, then it's going to be y equals log, what's the base? It's base 6. Okay, and the y is up here, and the x is by itself, so it's going to be the opposite. The y is by itself, the x goes here. All right, I'm just going to give a little challenge here. Let's say we have the equation y equals 13 times 4 to the power of x plus 9. And I want to know when that, what x has to be for y to equal, let's say, 104. Okay, what value of x will make that equal to 104? So I'm going to put in 104 equals 13 times 4 to the power of x plus 9. Okay, well, let's subtract 9 from both sides. So 104 minus 9 is 95. 13 times 4 to the power of x. Let's divide both sides by 13. Okay, so 95 divided by 13, that's about, I don't know, 7 point something. So 4 to the power of what gives you 7 point something? Well, 4 to the 1 gives you 4. 4 to the 2 gives you 16. That's too much. So it's 1 point something. All right, so that's going to be too hard to find out. We're going to have to do so much trial and error to find out 4 to the what gives me 95 over 13. So we need to do the inverse operation. So we're going to take the log of which base? Okay, I'm going to say the base, but I want you guys to say it before me. So what base are we doing? This is the base of 4. It's 4 to the power of x. We're going to do log base 4 of 95 over 13 equals log base 4 of 4 to the power of x. And the log base 4 of 4 to the anything is just itself. That's the actual, it's like saying the sine inverse of sine of 84. What's that equal to? Well, it's just, that equals just 84. Take the sine inverse of the sine, you just get 84. Okay, so here we have log base 4 of 7 point something is equal to x, and that's your answer. Okay, now, there's a very good chance your calculator doesn't have log base 4. Some of them do, some of them don't. Some of them just might have the log button, and that's log base 10. Don't use that button for log base 4. It won't work. There are some tricks that we're going to teach you so that you can use that button. You would actually have to just do log of 95 over 13, but then you'd have to divide by log of 4. These are both base 10. So that's actually a trick that we're going to learn later, and that will actually give you the same answer. And we'll show you why that works later. But if you just want to be crafty and you don't have a good button and you don't have access to a computer that has logs with a base in it, just do log base 10 of this number divided by log base 10 of this number. We'll show you why that works in the next few sections. All right, so my calculator is not very good, so I just did the log of 95. So I put in 95 over 13 equals, and I took the log of that, divided by 4, took the log of that, equals, and I got 1.43478 approximately equals x. Let me test that out. Let me see if that actually works in my answer. I'm just going to see a 4 to the power of this. See what that equals. I'm just going to keep the number in my calculator to have it exact. So 4 to the power of that answer equals 7.30769. What does that equal to? Let's multiply that by 13. And we got exactly 95, right? So this is exactly 95 over 13. So it does work. All right, let's just keep practicing writing, going back and forth. So let's say we have y equals log base 5 of x. What is that the same as saying? Okay, well that's the same as saying that, so this is the base 5, so I know it's going to be 5 to the power of something. Now, I see that the 5 and the x are right next to each other here. When I change it, it's going to be 5 to the y, and that's going to be equal to x. So when you change it from the log to the exponent, these are the exact same equation. If you were to graph these two things, it would give you all the exact same graph. They're not inverses of each other. These are actually the same as each other. The inverse of each of these would be y equals 5 to the x, and x equals the log base 5 of y. So these are the same, and these are the same, and they are inverses of each other. Okay, so y equals 5 to the x looks like this. Y equals 5 to the power of x. So if I plug in x is 3, I'm going to get 125. 3, 125. X equals log 5, log of y base 5. That shouldn't look like an exponent. This should be on the same level. Log of y base 5. That also looks like this. But we don't like having x by itself in any equation. So this isn't really one that we're going to use. We would want to rewrite this. And so we would have to we'd have to do 5 to the power of x. Do 5 to the power of x equals 5 to the power of log base 5 of y. Sorry, and that, if you have 5 to the power of log of 5, those are just inverse operations. So that's just going to equal y. So y equals 5 to the x. As you can see, it's the exact same thing. All right, whereas x equals 5 to the power of y is this guy here. Or you can say y equals log base 5 of x, right? Which is the way we're used to seeing this. This is y equals log base 5 of x. So log of x base 5. All right, just trying to do as much with these to get you guys comfortable with stuff that you're going to see. Okay, let's start evaluating something. Let's say, what does log base 2 of 128 equals? I just want you guys to guess right now. I'm going to take a few seconds, let you maybe pause the video. Guess what that's going to equal. All right, so let's just let it equal y, or whatever variable you want. Let's let it equal p, so it's not confusing. Okay, so we can rewrite this in exponential form, right? So I see that the base is 2. That's what I always start with. That way I never make mistakes. So I know it's 2 to the something equals something. Okay? The 128 and the 2 are next to each other right now. So I know that when I do the conversion, they're not going to be next to each other. So do not put a 128 here. 128 goes here, and P goes here. So this is the exact same thing. So this is the same thing as saying 2 to the what gives me 128. Okay, well, let's try it out. 2 to the 1 will give me 2. Right? 2 to the 1 is 2. 2 squared is 4. 2 to the 3 is 8. 2 to the 4 is 16. 2 to the 5 is 32. 2 to the 6 is 64. And 2 to the 7 is 128. The answer is, this P has to equal 7. Right? So log base 2 of 128 is equal to 7. It's saying what is the answer to any log is just the number that base has to be raised to get that number. All right, let's try another one. Log base 3 of 81. Pause the video and you tell me what you think that answer is going to be. All right, so I know the answer is just going to be 3 to the what gives me 81. Well, I know 3 to the 1 is 3. 3 squared is not 81. 3 to the 3 is not 81. But 3 to the 4 does equal 81. So this answer is 4. All right, what if I just said log of 1,000,000? Tell me what you think that equals. Pause the video and come back to me when you think you're ready for me to give you the answer. All right, I didn't give you a base, so we assume that the base must have been 10. All right, so just the fact that I didn't give you a base means that the base is 10. Well, 10 to the what gives me 1,000,000. Well, 10 to the 0 gives me 1. 10 to the 1 gives me 10. 10 squared gives me 100. 10 to the 3 gives me 1,000. 10 to the 4, it's just basically the number of zeros is the answer. 4, 5, and 10 to the 6. So this is just equal to 6. All right, here's another challenge. Log base 5 of the square root of 5. Pause the video, see if you can get it. Okay, remember, we're just saying 5 to the what power is equal to the square root of 5. Well, since the square root of 5 is exactly the same as 5 to the 1/2, well, then their answer is 1/2. 1/2. So the answer here is 1/2. All right, let's try another one. Log base 7 of the 6th root of 7 to the power of 9. Pause the video, see if you can figure out what that is going to equal. All right, now that you're back, well, I think I know that the 6th root of 7 to the power of 9 is just so we got 7 to the power of 9 over 6. If you remember from grade 11, right? I know the 3rd root of 7 is just equal to 7 to the 1/3. So the 3rd root of 7 to the power of 4 is just 7 to the power of 4/3. In this case, we got 7 to the power of 9/6. So we're saying the log base 7, so it's saying 7 to the what gives you this, which is 7 to the 9/6. Okay, well, the answer is 9/6. All right, we'll do one more, a trick question here. Let's do log base 5 of -7. All right, pause the video and see if you can get this one. All right, now that you're back, it's not going to give you an answer. You can't do this. If you think about it, we're basically answering the question 5 to the what gives you -7. Well, here's the graph of 5 to the anything. right here. Where does it give you negative 7? It doesn't. It's always positive. The log base 5 is right here. Negative 7 is over here. There's no value. It stops at the y-axis, right? So this does not exist. Even if I put the log of any negative number here, it's not going to work. Even if I put 0, this would not work. Okay? But any positive number will work because it goes down like any positive number. It starts off at negative infinity at a very, very small positive number, and it goes all the way off to infinity. So all these values will work. They're all in the domain, but 0 and to the left are not in the domain. All right, just going to finish off. I'm just going to give you a logarithm here. T equals u to the power of v. I want you to rewrite that as a logarithm, but the exact same equation, just with a log. I also want you to write the inverse function of that, considering that, I should make it x and y so you know what the inverses are. So let me try that again. Y equals u to the power of x. Right, so I want you to write this exact same equation in the log form. I want you to write the inverse function, and then I want you to write the logarithmic version of the inverse function. So pause the video, see if you can do it on your own, and come back for the answer. All right, so let's start off with the logarithmic version of this one. So I know immediately that the base is u. So I'm going to put u, not u as in me and you, the letter u, right? I see, and this is just how I do it, right? I know that the u to the x is right here, and I know that's not going to be the case for my log function. So obviously, I need to put the letter y here. You switch it up. And y is by itself over here, so that's where I'm going to put the x. So the one thing that I do first is I make sure that the base is the base. That, because there's so many kids that will just randomly put u, x, y anywhere. So the very, very first thing I want you guys to put is the base as the base. And then the thing that is associated with the base, that's a little bit above the base, is going to be not the thing that's above the base anymore. Okay, that's where you have to switch it. And these are the same function. This is not the inverse function. This is the same function. Right? The inverse function of this is when you switch the x and y. So x equals u to the power of y. Or let's do the logarithmic version. So the log version, you just write the word log. Make sure the base is the same base. So the base is u. There you go. The variable that's right next to the u will not be next to the u. That goes to the other spot. And the one that's not next to the u is next to the u. Now this is not an exponent, right? This is on the same level as x, and this has to be a subscript lower. Right? So make sure you write it with good form. And you can see in the textbook how they write it, so much less sloppy than me, but I want you to follow that and do it properly. Okay, one more thing I wanted you guys to mention, just so like you're not too curious about it and your question never gets answered. When we taught you about exponentials, we often taught you about like an exponential with a value between 0 and 1, and we taught you that that curve kind of does this. We taught you exponentials with a value of greater than 1, and we taught you that curve kind of does this. And whoever your teacher was, I don't know if they skimmed it over or what. Sometimes like it's not really part of the curriculum to show you anything. So what if you actually have the value of 1? Well, that's not even an exponential, because 1 to the anything just equals 1. That's just a straight line. All you have to, that's just the same as saying y equals 1. So this is not an exponential function. Not exponential. That's something else. That's just a linear function of degree 0. Not exponential. Okay. Also, what if you have a negative number in there, like negative 4 to the power of x? This thing acts so crazy, and it's not something that we study in high school. I have no problem if you have the natural numbers, like negative 4 to the 0 is 1. right? Y equals negative 4 to the power of x. Negative 4 to the 1 is negative 4. Negative 4 squared is positive 16. Now this starts going up and down. But what makes it even worse is we know that when x is an even number, this is going to be positive. We know when x is an odd number, it's going to be negative. What about when it's between the two? Like what about at 1.5? What about at 1.7? It gets super crazy. It is not something that we study. It is not an exponential. Okay? So the same time, this right here is your base. We will not be talking about a negative base down here. You'll never see a negative down here. And you won't see a 1 down here. Okay, the base of 1 and the base of negative 4 is not, they're not exponentials. Okay, so we do not study negative numbers in there. It's too crazy, and it's not something that we want to be touching in grade 12 curriculum. Okay, so you will notice that you're always going to get a base that is between 0 and 1, not inclusively, or greater than 1. Okay, you're never going to get a negative base. No negatives. You're never going to get a 0. No 0. And you're never going to get 1. No 1. Of course, if you got 1, it wouldn't be that big of an issue. But the only answer you can give is 1. Right? So it's just dumb. Because as soon as you put any other number here, there's no answer. 1 to, like let's say you put a 1.2. Well, 1 times 1 times 1 times 1 times 1, like 1 to the what power gives you 1.2? Well, nothing. 1 to the anything gives you 1, right? So that you can't have a 1, you can't have a 0, you can't have a negative. That's not logarithms. Okay, so when we're studying logarithms, you're always going to see numbers between 0 and infinity, not including 1. All right, guys, I'm fully aware that all my videos are super messy. I hope that you get something out of it anyways. Feel free to give me comments. If it's too messy for you, then I'll just change. Like I don't mind doing it. I'll take the extra time to make it less messy. But if this is sufficient, then I don't want to go out of my way to do, to clean it up too much when I could be spending my time doing other things. Okay, so I hope that's good for you guys, and I'll see you again for the next video.